Hello everyone, this is Giacomo Beccari speaking, and I'm happy to welcome you again to the new colloquium of the ESO Hypatia Colloquium series that is dedicated to early career scientists, early career astronomers. We congratulate all the time. We would like to congratulate with the speakers for being with us today, for being selected, and I would like to immediately thank the chairs of today, who are two, Francesca and Amanda, who are two two PhD students hosted at ESO Garkin and Chile. So thank you very much for your help and congratulations. Very quickly, just to let you know, as you might now be familiar with this form, basically with the two speakers, they have 30-minute slots, which includes the 20 to 25 minutes talk plus question at the end. The question will be moderated by our chairs, and you can make a question either using the chat on inside raising the hand actually inside Zoom, or you can use the chat on YouTube if you're following the event on YouTube. For people that are in Zoom, please be aware that we are streaming this event live on YouTube. So if you are uncomfortable, I will ask you to please leave the event, and then you can still follow on YouTube. And then I encourage everyone, please go on our Hypatia pages where you see the program of the event, and for each of our speakers, you can download not only the abstract, but also the curriculum, a CV of our speakers, so you can meet them and get closer to their profiles. Finally, I would like to make an announcement that just an ESO announcement. We have now opened the call for studentship programs. So we encourage PhD students who plan to come to ESO you can come and spend from 6 months up to 2 years to do your PhD thesis together with a supervisor at ESO. So for this particular program, you need to be already enrolled in a PhD program at a university, but you can spend this amount of time basically within ESO under the supervision or the help of a ESO faculty member, or also together with an ESO fellow. So you can join our community. We are looking forward, and the deadline is the end of May, 31st of May. So please, we encourage to apply. If you have any question, you can contact me or the Office of Science. There are all the references in our web pages. You can go to the job recruitment portal of ESO. You see the link to the announcement, and so you can also then ask all the questions you might have. So with that, I would like to then give the floor to Amanda. Please, Amanda, you can start introducing the first speaker and start the event. Thank you very much.
Hello everyone, I'm Amanda, and it is my pleasure today to introduce Paulina Karczmarek. Paulina is a postdoc from the Universidad de Concepción in Chile. She did her undergrad and her master's at Nicolaus Copernicus University in Poland and got her PhD from the University of Warsaw. She's part of the Araucaria project, which is an international project devoted to precise and accurate calibrations of the cosmic distance scale based on distance measurements to various galaxies in the local group. The focus of her research is on pulsating stars like Cepheids and RR Lyrae in binary systems. Her talk today is titled "The Impact of Classical Cepheids Companions on the Extragalactic Distance Scale." So you can go ahead, Paulina.
Thank you very much, Amanda. Thank you for this introduction. Now let me share my screen. And please confirm that you see it. Can you see the screen?
Yes.
Yes.
Perfect. Okay. I am very thrilled and honored to present to you today the results of my recent work on binary Cepheids and how the companions to those Cepheids impact the way we measure distances using Cepheids. And as you already, Amanda, said, this is a big part of the Araucaria project work. And this is already a 20-year project and international. We join people from Chile and Poland and France and a few other countries. And we determine distances in order to calculate the best way possible the Hubble constant. Hubble constant is the single most important value that we can learn about our universe, because it tells us about its age, its size, its content, its fate. And the more precise we know it, the more we know the universe that we live in on the most generous, the grand scale. But the problem is we cannot measure the Hubble constant directly, but there are indirect ways to measure it. And the way I present to you is the cosmic distance scale. So this is a group of interlocked methods that are used to calibrate one another and in the end to determine the Hubble constant. This is not the only way we can measure Hubble constant, but this is the most famous and popular one because it's also the shortest way. So all the methods have their limitations and they have their usefulness range. For example, parallaxes are great to determine distances up to a few hundred parsecs. So they're very good to determine distances in our local neighborhood. While supernovae type 1a, being one of the most luminous events that we can see in the universe, are perfect to determine distances further away. The problem is we cannot really measure any supernovae, the distance to any supernovae, using parallax, because we don't have supernovae exploding in our local neighborhood. And maybe that's a good thing, because that will have dire consequences on the life on Earth. Luckily, we can join two methods using some kind of intermediate methods. And for this, we can use Cepheids. So we can measure parallaxes of a few closest Cepheids to us, and then use Cepheids to calibrate the supernovae type 1a events. And for that, and in the end, we can measure the Hubble constant. Now, the problem lies with the errors that we can make on the way. So if we make an error in determining distances using parallax or Cepheids, that errors will be propagated onto next methods, and in the end, it will enter the total error budget of the Hubble constant. And if we want to know the Hubble constant as accurately and precisely as possible, we have to take care of minimizing and taking into account all the methods, all the errors that we can make in the process of determining distances. And minimizing those methods will lead us to the more accurate determination of the Hubble constant. So what errors are we talking about when we are talking about Cepheids? Well, Cepheids are famous for their period luminosity relation that is also called Leavitt law, because it was discovered by Henrietta Leavitt and reported in her paper in 1920, so more than 100 years ago. And what she noticed is that Cepheids, which are evolved giants, pulsate, and they follow the period luminosity relation in a way that Cepheids who have longer pulsation periods have on average also larger brightness, and Cepheids who have smaller pulsation periods are dimmer. And this is about their absolute luminosity. So they are basically designed in this way. What you can see here is the plot from her paper. And on the x-axis is the logarithm of pulsation period in days. And on the y-axis is magnitude in photometric plate. And period luminosity relation belong to two different galaxies here, to the LMC and SMC. And you can see that Cepheids from the SMC follow a little bit different period luminosity relation, meaning that they are dimmer. But they are not dimmer by their nature, they are dimmer just because they are further. And this is a beautiful way to determine distances. If we have two different galaxies that host Cepheids, we can measure their brightness, create period luminosity relation, and then calculate the difference between the intersects of period luminosity relation with the y-axis for both galaxies. That difference will tell us about the distance between the galaxies. Now, let's introduce a companion to a Cepheid. So let's imagine there is a Cepheid and it has a bright companion. What we expect is that companion will add its light to the Cepheid, and in the end, we would see a Cepheid a little bit more brighter than the rest of the Cepheids, that the rest of the stars on the period luminosity relation. As long as this is just one Cepheid, there is no problem. We can basically ignore it and still calculate the period luminosity relation. When it gets tricky is when we can have more than one Cepheid. For example, maybe all of them, maybe half of them are binaries. And in such a way, we will now draw the period luminosity relation that is on average higher than the one we would draw for just single Cepheids. And that introduces a systematic error. And my job here is to determine what is the size of this error, how wrong we are if we include binary Cepheids instead of just single Cepheids. So let's look at some binary Cepheids that we know of. There was a study conducted by Nancy Evans in 1992 that showed that basically 60 to 80 galactic Cepheids in our Milky Way should have companions. And the way she did that was that she did a ultraviolet survey among the closest Cepheids to us. And what she discovered that there is the excess radiation in the ultraviolet range, meaning that there are not Cepheids who produce this excess radiation, but they're probably their hot main sequence companions. Hot because they shine in the ultraviolet, and main sequence because we cannot see any other interaction with those companions. For example, eclipses. So the companions have to be really tiny compared to the Cepheids. But when we measure particular Cepheids in our galaxy and LMC and SMC, we get totally different story. We see that in the Milky Way, we have a database of 170 binary Cepheids. In the LMC, we have only 25, and in the SMC, it's even worse. We have just 4 binary Cepheids, but 5 other firm candidates. And that poses a problem because in the Milky Way, we have more than 2,000 Cepheids in total. In the LMC, we have more than 3,000 Cepheids, and in the SMC also more than 3,000 Cepheids. So if we expect 60 to 80 all of Cepheids to contain, to have a companion, but we only see about 6 of them having companion in the Milky Way and less than 1% of the LMC Cepheids to have a companion, we are missing a lot of binaries. And the question is why? Well, because we suffer observation and completeness biases, meaning that those Cepheids, 60 to 80%, were discovered because the ultraviolet light excess from the companion. And the ones in the LMC and SMC were discovered because of the eclipses or the radial velocity curves that show the orbital period. But if we don't have this information, we are basically blind, and we cannot even assess the impact of binary Cepheids if we cannot find all of them. Luckily, we don't have to observe them all. We can simulate them. And this is where the binary population synthesis method comes into play. And this is a great method because it's free from selection and completeness biases. I have all the binary Cepheids that I can create. And also the percentage of binary Cepheids in this method is controlled by the so-called binarity parameter, which is a value that ranges from 0 to 100, 0 being all Cepheids are single and 100 being all are binaries. And it's fast and efficient. So I can simulate whole populations of binary Cepheids. Like in tens of thousands, not only a few thousands or a few hundred of Cepheids. Well, it has its own limitations too. So people argue that it's maybe too simplistic evolution of single and binary stars, because it's just an approximation of how the stars would evolve according to their evolutionary tracks. And I agree with that, but this method is not for modeling particular systems, is to create a whole population of stars so that we can measure and investigate their statistical features as a bunch. And this is exactly what we are trying to do using period luminosity relation of classical Cepheids. We measure a lot of stars at once, so this tool is perfect. It comes also with some limitations, like I have no pulsation periods or magnitudes in this method, but this can be done using external codes. And last but not least, this method is dependent on input parameters and processes. So whatever is in the code will generate some result. That's why I created not one simulation, not two, but 16 different variants of synthetic populations for 3 different metallicities. So for that, I'm hoping I will account for and cover all the differences in the populations of binary Cepheids that we know and we don't know of. So the outline of my project is that, first of all, I wanted to compare the results that I achieved with synthetic population with observations, so I know that my models are reliable. Next, I wanted to determine the thing that we were waiting for, so the shift in the 0 point of period luminosity relation due to Cepheids companions. And finally, I am very thrilled to share with you a tiny glimpse into the future and detection of binary Cepheids on the color diagram. This is still work in progress, and the results are preliminary, so you will be my first audience to actually see it. So let's compare with the observations. This is the thing that I call the sanity check. So we want to know that our results are actually good before we introduce some more complications. And the simplest way we can check if our results of synthetic population of Cepheids are correct is to compare the period luminosity relations of just single Cepheids with the ones from the literature. And here in different colors, you see different period luminosity relations in different passbands. So we have the B band, V band, IJ, HK, and Wassenheit index, which is a great mixture of V and I bands that is reddening free. And you can see the period luminosity relations here, and the fit, the linear fit, is given by the slope and the 0 point. For now, what I'm interested in is the slope of such relation. And I just want to make sure that this is pretty much the same as the one reported in the literature. And I'm relieved to tell you that yes, it is. The values that you can see here in the bottom are the slopes of the period luminosity relations that I achieved from my synthetic populations. And they're pretty much similar to the ones that you will read about in the literature. So now that we know that our synthetic populations reflect the real Cepheids really well, let's add companions and let's see what can happen. What can happen is that we will see a lot of outliers above the period luminosity relation, and this is actually expected. This was shown in the great work of Bogumił Pilecki from 2021. He is also a member of the Araucaria project. And he had that hypothesis that Cepheids that are above the period luminosity relation are probably binaries. And this is the similar picture that I showed you at the very beginning, that the companion adds so much light to the Cepheid that it puts the Cepheid way above the period luminosity relation. So his idea was that probably majority of all those outliers are binary Cepheid with some giant companion, or at least very luminous companion. And he checked that by conducting spectroscopic observations, and he reported that indeed are binary Cepheids. Now, what I see from my synthetic populations when I put the binarity parameter to 100 is that I also see those outliers. They are way above the period luminosity relation. What I also see in my simulation that cannot be seen in the observations are those tiny yellow dots above here. And they are yellow, and yellow indicates here that the Cepheid lost its all observed amplitude of pulsation. It still means that it pulsates, but it's so overshined by the companion, who in this case can be like asymptotic giant branch star, so much more luminous, that even the ups and downs in the light curve of Cepheid are basically dumped, and we don't see even those. That's why the stars, like here, won't be visible on the period luminosity relation, because they will show no visible pulsation to us as observers if they have such bright companions. On the other hand, we have Cepheids that are marked as navy blue here, and they're also binary Cepheids, and they have companions. But companions here add really little to the total light of the Cepheid. But maybe the cumulative light from all those companions, from all those Cepheids, can shift a little bit the period luminosity relation upwards. Unfortunately, we cannot check it with observations, but we can check it with simulation. And the way I do it is that I created a parameter that tells us how much the 0 point can be shifted. And this is just called 0 point difference. So this is the difference between the 0 point, here the intersect, that period luminosity of Cepheid, of just single Cepheids would have, compared to the period luminosity of binary Cepheid of some percentage. So this is 0 point with some percentage of Cepheids. And we expect that if it's moved a little bit upward, if it's shifted upward, then the difference by this definition will be negative. And indeed, this is something that synthetic population shows us, that this 0 point shift should be more negative the more percent of binary Cepheids we have in the sample, but also it should be more negative for blue and visible passbands, while much smaller in the near infrared and Wassenheit index. But this is not actually the way we measure distances, right? Because the way we measure distances is we take two different period luminosity relations of two different galaxies. So the way I can measure the change of this distance modules, the distance between the two period luminosity relations, is by setting some standards, some reference points. So at this point, I have distance modulus reference 1. And now I can imagine maybe in the Large Magellanic Cloud, we have more binary Cepheids, not only all the single ones, but like 50% is binary. So this period luminosity relation will be shifted a little bit up, and therefore the distance modulus that now will be created between the Milky Way with 0% of binary Cepheids and LMC with half of binary Cepheids will be smaller. And therefore the difference between the two should be negative. And this is what we actually see from the synthetic population. And we see that this shift is at most 200th of a magnitude. And this is if we have 100% binaries in the LMC, while 0% binaries in the Milky Way. But wait, we already know that in the Milky Way there should be 60 to 80% of binary Cepheids, right? So let's do another exercise, and this time let's assume that what changes is the number of binary Cepheids in the Milky Way. But in the LMC, it stays the same on the level of 0. And with this, the new distance modulus that we would achieve will be a little bit larger than our reference one. So the difference between the two should be positive. And this is exactly what we are seeing. And now the values are of order of 100th of a magnitude. Now you probably see where this is already going. So let's just fill this matrix with all the numbers. And this is how it looks like. This shows how big of an error we're gonna make if we assume some kind of binary percentage in our target galaxy, this time LMC, and in our reference galaxy like Milky Way. So as you can see, we can make the most of 200ths of magnitude error when we assume binarity of, let's say, 100%, when in our Milky Way it's 0%. And these are the results that I have in the V band. But usually we don't measure the distances in the V band. We use it in the near infrared for many good reasons. One of them being now that the difference, that the value of this difference of the 0 point is much smaller in the near infrared. So let me just move now to the I band, and you can already see that those values are getting much smaller. And now we are in the K band, and this is the near infrared. So as you can see, if we assume that the percentage of binaries in the Milky Way is like 75%, because it's somewhere in between 60 and 80, we can make the error, which is of the magnitude of 1 millimagnitude plus minus 1 millimagnitude. And this is very good news, because that means that in the near infrared, the effect of binaries, binary Cepheids on the period luminosity relation is really not so large. Now, when we go to the Wassenheit index, it gets even smaller. So these are two very good tools to use to measure distances, even with Cepheids, binary Cepheids included. What is the effect on the Hubble constant? Well, as you can see, actually very tiny. This line shows the 0.003 magnitudes, so 3 millimagnitudes difference that can be made if we take into account the binarity of companions. And this stripe shows just the Hubble constant that we know is the most accurate up to date, with 1 sigma, so with 1 kilometer per second per megaparsec. And this black line shows how this 0 point shift would affect the Hubble constant, and at the value of 0.003 magnitudes, it doesn't affect it really in any significant way. But at least now we have measured that. So now I will just finish my presentation with showing you a little bit teaser trailer how we can detect binary Cepheids, because this synthetic population of binary Cepheids allowed me not only to assess their impact on extragalactic distance scale, but also to learn a little bit of how we can better detect them, especially when Vera Rubin Observatory comes along and does the multi-wavelength study survey of the entire sky and also Cepheids. So what you can see here is a Cepheid on the Hertzsprung-Russell diagram. And what you can see here is the Cepheid companion, which is just a constant star. Now, the Cepheid wobbles around the period luminosity, the Cepheid wobbles around the instability strip here, and you can see those movements as the changes in the color of the Cepheid, as described here in the B minus V versus U minus B color diagram. And if a Cepheid is single, it just makes the movement like this. But if the companion is involved, especially if it's very bright and hot companion, the Cepheid path will change into more loopy one. So this is how we can not only detect the companion, but I also hope we can measure some properties of the companion just by looking at the shape and size and location of such loop. So what I'm leaving you with is the summary. And the summary has three very important points. First of it, the results of my synthetic populations are consistent with observations, both relating to period luminosity slopes and outliers above the period luminosity relation. And this is great because we now know that synthetic populations can reproduce the qualities of Cepheids very well and are bias-free. So we can use them even if we don't know the binarity percentage in Cepheids that we observe. Second, I'm already finishing. Second of all, the difference in the 0 point between some Cepheids of different percentage depends on this percentage of the reference and target galaxy and the wavelength, and is the smallest in the near infrared. So we see the maximum change of 2 or 3 millimagnitudes in the near infrared and Wasson height index, and that is negligible, but now at least quantified. And this is the biggest contribution. And finally, last but not least, the binary Cepheids can make loops on color diagrams, and those shapes may reveal characteristics of the companions. But this is work in progress, and stay tuned for the results that I will present in the future. Thank you very much.
Thank you, Paulina, for the lovely presentation. Do we have questions? If we don't have questions, I have questions.
Go ahead.
So I was wondering, how do the errors combine? Because you said that, I mean, you can measure parallax and then you can use the Cepheids and you can also use the supernovae. How do your errors of the stuff that you measured to quantify combine with like the supernovae method? Like, how do they add up to the error of the Hubble constant?
Exactly. So this is what I showed here a little bit. This is the contribution of my error to the Hubble constant. As you can see, it's really tiny. So we are talking about the small difference between the dotted line and the solid line when it meets this one, right? So this is really tiny contribution. But at some point, we are hoping to reduce the errors associated with the Hubble constant even more. And maybe there will be a moment in the future when binarity has to be taken into account, because all the other errors and uncertainties connected to it will be so small that now the binarity will be a significant factor. So far, to the best of my knowledge, the calculation of the error of the Hubble constant as done by Rees does not include the binarity of Cepheids into the calculations. So that would be, an important thing to add sometime in the future once we reduce this error that is now associated with the Hubble constant even more.
Thank you.
For now, it's like less than 1%, much less. So there's nothing to be worried about so far.
Hello.
Yes,
Hello.
Giacomo.
Yes, I am Pradeep from India. I have one question that Paulina have presented that companion of Cepheids. So these companions should be Cepheids or other type of star?
So who are the companions? That's your question?
Yes. My question is, what type of companion did you consider in your presentation?
Okay, that's a perfect question. I'm very happy you asked it. Basically, all types of companions, and with the synthetic simulation, we can learn what those types are. I have some additional plots to show you. So, for example, this is the insight in the companions of Cepheids. as I told you, I have so many variants of synthetic populations. They're called set A, but I also have set B, C, and D. And all those stripes represent different variant of a simulation. So just don't freak out because it's so many, but more focus on colors. And the color here, the navy blue, represents the main sequence stars. So vast majority of companions to classical Cepheids and binary systems are main sequence companions. Now we have a little bit of red giants and horizontal branch stars. So they're as evolved as Cepheids. Then we have a little bit of white dwarfs, tiny little bit of neutron stars, and some other things that weren't just included into this plot. And as you can see, this this percentage varies on the model that I used, on the variation, but in general we have still majority of main sequence companions, which is what we know from the literature that has been observed. And also that translates to the spectral type of the companions, which are again in majority the B and A type stars. So they're hot main sequence stars. The same comes from my synthetic simulation as was observed by Nancy Evans.
Do we have time for one more question, Giacomo?
Yes, there is a question from YouTube. I posted it. Maybe you can.
Okay, so this is a question from Camilla. She says, thank you very much for the nice talk. And her question is the slope of the PL relations not affected by the Cepheids with companions?
Perfect question. Yes, it is affected, of course. But I will tell you that the errors that we have, like the uncertainty of the slope, are much bigger than the change in the slope. But this is very, very insightful question. I checked that. The answer is it is affected. It is a little bit affected, but not so much that we should be worried about. In the end, we try to measure distances. We measure distances using classical Cepheids, and imagine if classical Cepheid had different slopes in different galaxies, or like for different binarity percentage. That would mean that we cannot use this method to determining distances because the slopes are not the same. So there is some kind of trade-off between how accurate we want to be and how practical we want to be. So for now, I will support the practical part, saying that we can assume that the slope does not change because it just makes the computation of distance using classical Cepheids so much more easy. And I will add one more thing, that the metallicity of Cepheids changes their brightness too. And this is the effect that it's so much bigger than the binarity, that I personally think that we should first focus on that instead of assuming that the slope remains constant even with different metallicities of Cepheids.
Thank you very much, Paulina. I guess now we go to the next talk.
Okay, so I start speaking. Good morning from Chile, and good afternoon for the rest of the audience, who I guess is mostly from Europe. I'm Francesca Lucertini, PhD student at University Andres Bello here in Chile, Santiago, and I'm the host of the second talk, which will presented from Kateryna Kravchenko. I hope to pronounce it correctly, sorry. So Kateryna obtained her PhD at the University Libre de Bruxelles, where she developed a topography method to reconstruct atmospheric motion in stars. And currently, she is a postdoctoral researcher at Max Planck Institute where she is again studying about the tomography of evolved star atmospheres. Her talk today is about tomography of evolved star atmosphere. So Kateryna, please, can you share your screen and your presentation?
Okay, let me share. Oh, sorry. You can see my slides.
Perfectly, and we can hear you. So please go ahead.
Okay. So good afternoon, everyone. So first of all, I would like to thank the organizers for the opportunity to present my research at this colloquium, and also to thank to my collaborators for their valuable help in this work. So today I will talk about tomography of evolved star atmospheres. As a first step, let me introduce you evolved stars. So all stars form via gravitational collapse of large clouds of interstellar material. However, their further evolution strongly depends on the star's initial mass. So in case of low mass stars like our Sun, after leaving main sequence, the star becomes a red giant and then asymptotic giant branch. And during this phase, the star is characterized by extended convective envelope, which is blown off by strong stellar winds, forming planetary nebula with a white dwarf in the middle. In case of high mass stars, after leaving main sequence, they become red supergiant and then explode as supernovae, with a neutron star or black hole left at the end. This table summarizes main properties of AGB and red supergiant stars compared to those of our Sun. So you can see that they are characterized by high luminosities, low effective temperatures, low surface gravities, which result in extended atmospheres of an order of few hundred of solar radii. Interferometric observations of the stars reveal presence of large convective cells in their atmosphere, which are different from the small-scale granulation which we are used to observe in our Sun. In addition, they are characterized by very complex atmospheric dynamics with large amplitude convective motions and shocks, which affect the formation of spectral lines and produce asymmetries in the spectral line shapes. But why do we care about AGB and red supergiant stars? First of all, due to their high luminosities, these stars are interesting targets to be observed in other galaxies beyond our Milky Way and to be used as extragalactic distance probes, the so-called standard candles. Nowadays, we have different types of standard candles like Cepheids, supernovae, planetary nebula. And AGBs and red supergiants could be perfect candidates to be used as standard candles since they form period luminosity relation. And since relation is linear, by knowing the photometric period of a star, we can derive its luminosity. However, as you can see from these figures, the stars do not fall on one single relation, but rather fall into different branches. And these branches represent different pulsation properties of the stars. Therefore, it is crucial to understand the mechanisms behind the photometric variability of the stars in order to calibrate their period luminosity relation and to use them as standard candles. In case of red supergiant stars, they are particularly important in the context of their role as supernova progenitors. So current stellar evolution models predict different evolutionary scenarios for red supergiant stars, which result in different supernovae they produce. For example, stars with masses below 17 solar mass are believed to be progenitors of type 2p supernova with a characteristic plateau light curve. Stars with higher masses may proceed different evolutionary channels. They may move back to the yellow and blue part of the HR diagram, characterized by high temperatures, and explode as a different type of supernova. Therefore, it is very important to understand the evolution of red supergiant stars in order to better model and interpret the pre-explosion observations of supernovae. Finally, both AGB and red supergiant stars play an important role in the cosmic matter cycle. During their lifetime, they produce a wide variety of chemical elements via nuclear fusion in their cores. Then a significant fraction of their initial mass is ejected into interstellar medium via strong stellar winds and supernova explosion, driving galactic chemical evolution. AGB stars in particular are major sources of S-process enrichment of the universe, mainly by chemical elements heavier than iron. And these elements in turn serve as building blocks for subsequent star and planet formation. So to summarize, a good understanding of AGB and red supergiant stars is very important in the context of broad range of astrophysical questions. However, their main properties, such as photometric variability and mass loss, are still poorly constrained. Therefore, the aim of my research is to characterize atmospheric motions in these stars in order to better understand the mechanisms behind their photometric variability and mass loss. And this can be done with the help of a tomographic method. So tomography is a very powerful technique which is currently used in many scientific fields. For example, with the help of computed tomography in medicine, we can obtain images of slices through the human body. And as I will show you later, with our implementation of a tomographic method, we can make slices through the stellar atmosphere and extract velocity inside each atmospheric slice. So how the tomographic method works? As a first step, we select an appropriate 1D model atmosphere of an AGB or red supergiant star. This model provides us temperature and density structures from the stellar center to the outer atmospheric layers, which allows us to compute synthetic spectrum. As a next step, we compute the so-called contribution function, which tells us where in the atmosphere spectral lines form. Line formation is very sensitive to the temperature. Therefore, some spectral lines will form closer to inner atmospheric layers characterized by higher temperatures, while some other lines will form in outer atmospheric layers characterized by cooler temperatures. And this allows us to split the atmosphere into different slices, which we call masks. And each slice will contain positions of lines which form inside a given atmospheric slice. This figure, it's a bit better illustration of the mass construction process. So here, x-axis is wavelength and the y-axis is optical depth. The yellow color shows a particular atmospheric layer. The star symbols show spectral lines which form inside this atmospheric layer. And you can see that our mask will contain central wavelengths of all lines which form inside the yellow atmospheric layer. So when our masks are constructed, we can cross-correlate them with either observed or synthetic stellar spectra, and resulting cross-correlation function, or CCF, will provide us average shape and velocity of lines inside a given atmospheric slice. But how reliable are our tomographic masks, which are constructed from 1D static model atmosphere while applied to dynamical model atmosphere? To answer this question, we tested our method on 3D radiative hydrodynamic simulations of a star atmosphere. So this type of simulations are characterized by realistic input physics and reproduce effects of convection, which plays a central role in the structure, dynamics, and appearance of AGB and red supergiant stars. So as a first step, we have to prove that the masks constructed from 1D static model probe same atmospheric depths in the dynamical model. So this figure shows distribution of line formation depths in 1D model in red and in 3D simulation in blue for different masks. You can see that 1D and 3D line formation depths overlap in all masks, proving that our masks correctly probe different optical depths in dynamical atmosphere. As a next step, we have to prove that tomography correctly reconstructs velocity field in dynamical atmosphere. So to prove this, we constructed a synthetic spectrum from our 3D simulation and cross-correlated it with a set of tomographic masks. The resulting cross-correlation functions are shown here in black color. As a next step, we extracted velocities from the 3D model structure corresponding to optical depth ranges probed by the tomographic masks. And they are shown here as green histograms. And you can see that histograms well reflect positions of peaks of CCFs in all masks. And this means that tomography correctly reconstructs velocity field layer by layer. And this fully validates the tomographic method. So in the next part of my talk, I would like to show you how we apply tomography to different types of observational data. I would like to start from the pulsation type of AGB stars called Miras, for which the tomographic method was originally designed more than 20 years ago. And the goal was to detect and follow the propagation of a shock wave through the atmosphere. Here I show you an example of cross-correlation functions for a Mira star RT Cygni. Here, different columns correspond to different observing epochs and different rows correspond to different masks. So the innermost atmospheric layer is shown at the top and the outermost atmospheric layer is shown at the bottom. So you can see that some cross-correlation functions are double-peaked. And this line doubling is associated with the passage of a shock wave through the atmosphere, which we call Schwarzschild scenario. So according to this scenario, when shock is located below the line-forming region, all lines are redshifted since all the matter is falling down. When shock starts to propagate through the atmosphere, the line exhibits a blue shifted component corresponding to the rising material. And the intensity of a blue shifted component increases with respect to the red shifted component as shock approaches upper atmospheric layers. And when shock passes through the atmosphere, all lines are blue shifted. And you can see that in case of RT Cygni, the temporal and spatial evolution of cross-correlation profiles nicely illustrate outward propagation of a shock wave through the atmosphere. Now I would like to show you application of a tomographic method to observations of red supergiant stars in order to interpret their photometric variability. A bit of a context here. So red supergiant stars are characterized by semi-regular photometric variations with two main periods, a short one of an order of few hundred days and a long one of an order of few thousand days. So the short photometric period was proposed to be due to convection or pulsations, while the long photometric period was attributed to binarity or magnetic activity. We are focused on the short photometric period and propose our interpretation for it. To do so, we selected two red supergiant stars, Ceph and Betelgeuse, and observed them with the Hermes spectrograph, which is mounted on Mercator telescope in La Palma in Spain. So we obtained a time series of high spectral resolution and high signal-to-noise ratio spectra. And as a next step, we applied tomographic method to all our data by cross-correlating all spectra by a set of 5 tomographic masks. And this is an example of resulting cross-correlation functions profiles for Ceph. Different columns correspond to different observing epochs, and different rows correspond to different masks. So as a next step, we used this kind of CCFs to extract velocity field for each epoch and for each atmospheric layer. And this is how our result looks like. So the first two panels show velocities which we derive from our cross-correlation functions using two methods. So the top panel shows Gaussian fit of our CCFs. The second panel shows mean CCF shift. The dots of the first panel show secondary peaks of double-peaked CCFs. The bottom panel shows photometric variations as crosses and temperature variations as squares. And our temperatures we derived from TAO bands in our spectrum. So from this figure, you can see that there is a phase shift between velocity variations and photometric variations, as well as between velocity and temperature variations. This phase shift translates into hysteresis slopes in the temperature velocity plane. So we detect hysteresis slopes for 3 different time ranges, which are shown here as different columns, which correspond to gray shaded areas on the light curve. The time scales of our hysteresis slopes are 552, 310, and 840 days, which is very close to the short photometric period of MUSEP. So in case of Betelgeuse, the result looks very similar. So we see a similar phase shift between velocity variations and photometric and temperature variations. This phase shift translates into hysteresis slopes in the temperature velocity plane with the time scales similar to the short photometric period of Betelgeuse. So in order to interpret hysteresis slopes, we applied the tomographic method to 3D radiative hydrodynamic simulations of a red supergiant star atmosphere. So we constructed time series synthetic spectra from the simulation and did exactly same analysis as for MUSEP and Betelgeuse. And this is what our simulation shows. Again, we see phase shift between velocity, temperature, and photometric variations, which results into hysteresis slopes, which are very similar to those which we observed for Betelgeuse and MUSEP. And the time scale of hysteresis slopes matches the photometric time scale of a simulation. So this means that by understanding the nature of hysteresis slopes in simulation, we can better understand those which occur in real stars. And the use of 3D simulations gives us an excellent opportunity to actually see how velocity and temperatures behave along the hysteresis slopes. So this figure shows velocity maps for different epochs along the hysteresis slope. Here, blue color corresponds to rising material and red color corresponds to falling material. And this figure shows a clear distinction between the upper and lower parts of hysteresis slope, this higher part characterized by mostly rising material. This figure shows temperature maps for different epochs along the hysteresis slope. Brighter colors here correspond to higher temperatures. And this figure shows a clear distinction between the left and right part of hysteresis slopes, with the right part characterized by higher temperatures. So according to our velocity and temperature maps, the appearance of bright hot regions on the stellar surface are followed by the material rising at the same location. And this accounts for the phase shift between velocity and temperature variations, and therefore for the hysteresis slopes. So according to dynamical picture in 3D simulations, the hysteresis slopes can be interpreted as follows. Convection produces acoustic waves in the stellar interior. These waves travel through the star until they reach the surface and turn into shocks. The shocks then transfer the heat through the atmosphere, producing surface brightness variations and therefore hysteresis slopes. This means that acoustic waves might trigger hysteresis slopes and therefore account for the short period photometric variations in red supergiant stars. So in the remaining time, I would like to show you how we can combine a tomographic method with spectro-interferometric observations of AGB and red supergiant stars, with a goal to get a more detailed view on the structure and dynamics of the stars. Here I show you an example of our VLTI amber observations of the pulsating Mira star as ORI. So if we extract interferometric observables at wavelengths contributing to the tomographic masks and fit them with a geometrical model, we can measure geometrical extension of different atmospheric layers as shown in this figure. Here, different colors correspond to our tomographic masks. And this measurement allows us to recover a relation between optical depth scale provided by tomographic masks and geometrical depth scale provided by interferometry. This relation can also be compared to those constructed from 1D and 3D dynamical models in order to test and constrain them. In addition, the knowledge of the link between optical and geometrical depth scale can help us to measure the shockwave velocity in Mira stars, which has not been done so far. So in order to measure velocity of a shockwave propagation, we need to know the distance and time scale of a shock propagation. To measure the distance, we can apply tomographic method to spectro-interferometric observations of stars and recover the link between optical and geometrical depth scale, as I showed you in the previous slide. To measure the time scale of a shock propagation, we can apply tomographic method to time series spectroscopic observations of a star. And this would allow us to locate and follow the propagation of a shock wave from the innermost atmospheric layers to the outermost atmospheric layers, and thus derive the corresponding time scale. Finally, combination of a tomographic method with interferometric observations can help us to investigate the link between surface structures and atmospheric motions in HB and red supergiant stars. So similar studies reported so far reconstructed intensity and velocity images, but averaged over all atmospheric depths. With the help of a tomographic method, we can reconstruct intensity and velocity maps as a function of depth in the atmosphere. For example, 3D simulations predict different velocity morphologies for different observing epochs and for different atmospheric layers.
5 minutes are left.
Okay, this means that application of a tomographic method to interferometric observations would help us to get a very detailed view on the development of the velocity through the atmosphere and the link between velocity morphology and surface structures we see in the stars. And this would provide new constraints on current dynamical model atmospheres. So here is the summary of my talk. I hope I convinced you that the tomographic method is a very powerful tool, and the goal of my future research is to try to expand it to different astronomical objects, such as Cepheids and the exoplanetary atmospheres. And the latter will be possible with the help of future ELT instrumentation. So thank you for your attention.
Okay, thank you, Kateryna, for the very nice talk, and congratulations for the impressive work. Let's see if there are questions in the audience. If not, I can start. So I was wondering, as you say, the spectroscopy line form in different level of a stellar atmosphere. And with this method, if I get it right, we are able to constrain the properties of each level of the atmospheric, of the stellar atmosphere. So how is it possible to better constrain also the atomic parameters of each level? I mean, how can connect this technique for chemical abundances, and how can use this to improve chemical abundances estimation?
Okay. This is a very interesting question. So far, we never tried to play with different chemical abundances. For example, we thought to somehow link the tomographic method with measurement of abundances in red supergiant stars. But the problem is that you have to be able to disentangle the contribution of the dynamics to the line shape and the contribution actually of a given chemical elements. So in supergiants, it's very difficult to find clean lines which are not affected by the dynamics, because the dynamics will affect the depths, the widths, and shapes by making them multi-component, for example. So it would be very difficult to derive abundance from those lines. So one may try to look in maybe near infrared part of a spectrum where it might be easier to do this. But yeah, what we usually do, we use the atomic properties of lines and we insert them into our spectrum synthesis code, which later helps us to construct our masks. But indeed, it would be interesting to do the opposite way as well.
Okay, thank you. I don't see more questions in the chat. Okay, Giacomo.
Yes, Francesca, thank you. Thank you, Kateryna. I have a curiosity around this last slide and the expansion to the exoplanetary atmospheres in particular. Can you elaborate a bit? Because I was wondering how. So, is it at all feasible now, or you need to? I mean, you need to wait for bigger mirrors, basically, to do this.
So maybe one backup slide from actually Andrei Chiavasa could be useful. Yeah. So first of all, what we need are high resolution spectra of star plus exoplanet, which, for example, we can obtain while a planet is transiting the star. Then we can subtract the star spectrum and try to work with the remaining spectrum of a planet. Then we can, using, for example, a model of exoplanetary atmosphere, we can try to measure where different molecules form in this model atmosphere, and then try to cross-correlate. So, for example, we can construct mask for CO, another mask for CH, and another mask for H2O. And then we can cross-correlate this masks with the exoplanetary spectrum and try to recover information about the stratification of the atmosphere, for example, and also dynamics, which then includes winds, clouds, and a lot of other things. But what is important is that we need the high resolution, high signal to noise ratio spectra. Yeah. Of course, we can try, and we will try to do it on simulations, because we have a large grid of stellar atmosphere simulations, and we can use state-of-the-art models for the exoplanet atmospheres. So we can try already to see how in future we would apply method. But of course, getting observed spectra with a good quality would be very challenging. Yeah.
So basically what you do here, you subtract the component of the star, basically.
Yes.
Try to extract extracting isolating, say the planet component. Basically.
Yes. And then trying to slice through it and see what forms and where, and how fast it moves.
Wow. Very nice. Thanks.
Okay, do we have other questions? If not, I think that let's thank Kateryna again for her talk. And I don't know if Giacomo, you want to add something?
Yeah, just thank you, Francesca. Thank you, Amanda and Francesca, very much for chairing the session, and to Kateryna and Paulina for their talks, and congratulations, and good luck, and hopefully see you around in real life soon, now that luckily life is coming back to a kind of normality. So I wish you all the best, and please, to everyone, please have a look at again, let me emphasize, let's have a look at the curriculum of the speakers on the Hypatia web pages. And also, let me remind again that we have another aspect that I want to advertise. We have also a program to host early career scientists as a visitors at ESO. So you can come as a visitor to ESO. This is a dedicated format to early career scientists. So go to our web pages and at ESO, and you can see this visitor program dedicated to early career scientists, which is, as for the Hypatia, a PhD student up to, or let's say early career scientist up to 3 years from the PhD. For you, there is a dedicated visitor program. You can come to ESO, work at ESO for 4 months, up to 4 months. Please take advantage of this, apply. We are looking forward to welcome you all. And with this, I thank again everyone and see you next week. Bye-bye.
Thank you.
Thank you.
Thank you. Bye.